Okay, so good afternoon to all. Am I audible? Okay, so good afternoon to all. Let's start today's session. In last lecture, we studied about the again a combinational circuit, which is a parallel adder, parallel subtractor, and a parallel adder subtractor combined. Okay, so in that we learn about the 4-bit parallel adder and subtractor and the adder subtractor circuit. Okay, and also we are implement the parallel subtractor by using the full adder only, but by using the 2's complement method. And also adder subtractor, we are using the exclusive OR gate for that. Okay, and then we learn about the code converters. Let me show you, in which we learn about the binary to gray code converter, and also we learn about the BCD to XS3 code converter. So for that we have to focus on the truth table. Okay, we have to focus on the truth table. So first of all, we have to learn or draw the truth table of a 4-bit binary to gray conversion. And from the truth table, our output is a gray code, and the output is a G4, G3, G2, and G1. It is G4, G3, G2, and G1, and we have to check at which moment my G4 is 1, and when it is 1, what is my input min terms. So from that we can implement derive the equation of G4 in terms of min terms, same way G3, G2, and G1, and same that min terms or the output G4, G3, G2, and G1 we are implementing by using a K-map. Okay, and how we have to solve the K-map, I think all of you are now aware about that. Okay, so from that we are deriving the equation of G4, G3, G2, and G1, and from the output equation which we are deriving, which is G4 is equal to B4 and G3 is equal to B4 exclusive or B3. Same way G2 is equal to B3 exclusive or B2, and G1 is equal to B2 exclusive or B1. So this is the circuit which we are deriving by using a K-map. So we are deriving the reduce function by using a K-map, and so we have a SOP form, and that SOP form we are implementing by using a logic diagram. So this is the case. Okay. And also we learn about the BCD to XS3 code converter. We learn about the BCD to XS3 code converters. Again, we have to draw the table, or you can say make a truth table of the BCD to XS3 code converter. So when we have a BCD number, we have to add 0011, or you can say XS3, because we have to add 3 to the BCD code. And if you convert 3 of a decimal into a binary, then it is a 0011. Then it is a 0011. So from the table again we have the output x4, x3, x2, and x1, and from that you can see here the min terms is between 0 to 9 only. The min terms is in between 0 to 9 only. So the another 6, which is starting from 10 to 15, are the don't care condition, or you can say invalid condition for the BCD code. Okay, so here we have a don't care condition starting with 10 to 15. So we have the equation of again x4, x3, x2 and x1, and we are implementing that table of x4, x3, x2 and x1 by using a K-map and simplifying it. Then we have the equation of the x4 in terms of b1, b2, b3, b4. Also we have a value of x3, x2 and x1, and from that we are deriving the equation. From that we have the equation and we are implementing the equation by using AOI logic, you can say, which is AND or an invert logic. Okay. So now we have to learn about the comparators, and again the comparators are covered in almost all the labs. Okay. Then also we covered this in theory session also. So let's start about the comparator. Okay. So again, generally we have to focus on the 1-bit comparator and 2-bit comparator only. Okay, we have to focus on the 1-bit comparator and 2-bit comparator only. Now, what is comparator? So again, a comparator is nothing but it is a combinational circuit which is used to compare the two binary numbers. So the application of the comparator is the comparer. It is used to compare the two binary numbers. Again, we have three possibilities. Why when we are comparing the two binary numbers, we have three possibilities. Okay, suppose I have a two binary number A and B, and I have to compare its magnitude. I want to compare its magnitude. So it having a three possibilities. Either my A is equal to B, or my A is greater than B, or my A is less than B. So this is the thing. Okay. Then again, which is the gate which is used for the basic comparator circuit? It is a exclusive NOR gate. And why it is known as a basic comparator? Because the truth table of the exclusive NOR is when both the bit is same, either both are 0 0 or both are 1 1, then and then it will give the output 1, then and then it will give the output 1. For 0 1 it will give the output 0, for 0 1 it will give the output 0, and for 1 0 also it will give the output 0. Okay, so for 0 1 it gives 1, and for 0 1 it gives 0, and for 1 0 it gives 0. So it will give the high output only when both the input is same. If my both the input is 0 0 or my both the input is 1 1, then and then it will give the output 1. So suppose we have a two binary numbers A and B which having a 4-bit inside. So the 4 bits for A is A3, A2, A1 and A0, and 4 bits for the B3 is B3, B2, B1 and B0. It can be said equal. When it can be said equal? When my A3 must equal to B3, A2 equal to B2 and A1 equal to B1, and my A0 equal to B0. Then and then I can say that my A equal to B. Then I can say my A equal to B. Okay. So this is the symbol of the equality, and let me show you the wait for the 1 minute. Yes, this is the symbol in a circle dot. It is the symbol of the exclusive NOR gate, and in the circle, the plus sign, in the circle plus sign is the symbol for the exclusive OR gate. Okay, so this is the symbol of the exclusive NOR gate. So if my A3 is coincide with B3, my A2 is coincide with B2 and my A0 is coincide with B0, then and then I can say, my A is equal to B. Then and then I can say my A is equal to B. Okay. So let the next one is the one bit comparator. So one bit comparator means we have a two numbers A and B, but both the bit having a single bit inside. So A having a bit A0 and B is the B0. Okay. So there are three possibilities. Again, A greater than B, A less than B, and A equal to B. So if my A0 is 1 and B0 is 0, if my A0 is 1 and B0 is 0, then it is known as the A greater than B. And again, these all the combinational circuit are are work on the SOP function, sum of products, or you can say the mean terms. Okay. So in a mean term function, 1 means as it is and 0 means bar. 1 means as it is and 0 means bar. So the equation for A greater than B is A0 B0 dash, or you can also say that A0 B0 bar. But suppose if my A0 0 and my B0 1, then my A is less than B. Then my A is less than B. And for the A less than B, the equation is A0 bar B0. A0 bar B0. Or you can say A0 dash B0. And suppose if my A0 and B0 1 here there is some mistake. Also you can say if my A0 and B0 is 0 0. Okay, if my A0 and B0 is 1 also you can say if my A0 and B0 is 0 0, or you can say coincide to each other, then my A equal to B. Then my A equal to B, and the equation for that it is equal is indicated by the exclusive NOR gate. Equal is indicated by the exclusive NOR gate. So this is the truth table for the one bit comparator. So when my A is 0 and B0 is 0 0, so it is the same thing. It is the same thing. So my A is equal to B. For 0 1 my A is less than B. For 1 0 my A is greater than B. And for 1 1 my A is equal to B again. Okay. So for A equal to B is indicated by the exclusive OR gate. So here we are giving the input A0 and B0. So my A is equal to B. For A less than B, we have the equation A0 B0 bar. Sorry, A0 bar B0, A0 bar B0. And for greater than, my equation is A0 B0 bar. So this is the logic circuit. This is the logic circuit of the one bit magnitude comparator. Also, we have a 2-bit magnitude comparator. So, suppose in a 2-bit magnitude comparator, again, comparator is a circuit which is used to compare two numbers only. Which is used to compare the two numbers only. In two numbers, you have either 1 bit or 2 bit or you can say 4 bit. Okay. So here it is a 2-bit magnitude comparator. So in 2-bit magnitude comparator, we have a two numbers A and B, and it having a in A we have a 2-bit A0 and A1, and in B also we have a 2-bit B0 and B1. And here A1 and B1, A1 and B1 is the MSB, or you can say a most significant bit. So its weightage is higher than the A0 and B0. It's higher than the A0 and B0. So let us focus about the first rule, which is A greater than B. So if my A1 is 1, if my A1 is 1 and B1 is 0, then we do not have to focus about A0 and B0, because these are A0 and B0 is the LSB, or you can say the least significant bit. So if my A1 is 1 and B1 is 0, then my A is greater than B. Then my A is greater than B. Okay. But suppose now in second case, if my A1 and B1 is same, either both are 1 1 or both are 0 0, then we have to focus on the next bit, which is A0 and B0. Then we have to focus on the next bit, which is A0 and B0. Then my A0 must be 1 and B0 must be 0 for the A greater than B. Okay. Then my A0 must be 1 and my B0 must be 0 for the A greater than B. So for the A greater than B, we have the equation. So first equation is this: A1 1, B1 0. So A1 B1 dash. So A1 B1 dash, or we have another possibility, possibility number 2. A1 and B1 is coincide, means either both are 0 or both are 1. So for the coincide, we have the equation of exclusive NOR gate. So A1 coincide with B1. Then at that case, we have to focus my A0 must be 1 and my B0 must be 0. So the equation for that is A0 B0 bar. So this is the whole equation of the A greater than B. Less than B is the opposite to the A greater than B. Now we have to replace A with a B. We have to replace A with a B simply. Okay. So now in that case, if my A1 is 0, if my A1 is 0 and my B1 is, if my A1 is 0 and my B1 is 1, then we do not have to focus on the A0 and B0. Then my A is always less than B. But in OR condition, if my A1 and B1 is coincide to each other, what that means, either both are 0 or the both are 1, then the second thing is, then my A0 must be 0, then my A0 must be 0 and B0 must be 1. Then and then I can say my A is less than B. So again we have to derive the equation for the A less than B. So the equation of the A less than B, so the first condition is A1 0, B1 1. So A0 bar B1, or you can say A0 dash B1, or means OR gate, so we have to add the sign of plus. And A1 is coincide with B1, coincide is indicated by the exclusive NOR gate. And the second thing is A0 0, B0 1, so A0 bar B0, or you can say A0 dash B0. Okay. And for the equality, my A1 must be equal to B1 and my A0 must be equal to B0. Then and then I can say that my A is equal to B. Then and then I can say my A is must be equal to, then and then I can say my A is equal to B. So either A1 and B1 is 0 0 and A0 and B0 0 0. Then also you can say A equal to B. So my A0 and B0, and same way A1 and B1 both are coincide to each other, then and then we can say that my A is equal to B. So this is the equation for the A equal to B. This is the equation for the A equal to B. So we have a three equation. The first equation for the A equal to B, second equation for the A less than B, and the third equation is for the A greater than B. Okay. Okay. So this is the equation for the A equal to B. So A1 is coincide with B1 and A0 is coincide with B0. Then and then we can say my A is equal to B. My A is equal to B. Now for the less than, sorry, here for the greater than, focus on the third equation. So A1 B1 bar. So here the first AND gate is shows the A1 B1 bar, and then we required A0 B0 bar. So A0 B0 bar with A1 coincide with B1. So here we are taking the A1 coincide with B1, giving to the AND gate. Also we are giving the another two input A0 and B0 bar, and finally we have the sign of plus. So that sign of plus is indicated by the OR gate. So this is the equation, or this is the circuit for the A greater than B. And same way, this is the circuit for the A less than B. For A less than B, you can see here A1 dash B1. So A1 dash B1 giving to the another one AND gate. With another two AND gate, we have A1 coincide with B1. So we are taking the input from the A1 coincide with B1 and A0 bar B0. So another input is A0 bar B0. And again, it having a plus sign. So here we are adding the exclusive OR gate. So this is the logic diagram of the, that is the logic diagram of the 2-bit magnitude comparator. 2-bit magnitude comparator. So anyone having any doubt in comparator? If anyone having any doubt in a comparator, you will ask me a question in a chat session, or you can ask me a question by unmute yourself. Anyone having any doubt? And if it is no doubt, please write down clear, then I will move forward. So I think there is no doubt, because I didn't get any reply from the, or any response from the all of you. Let me move ahead. The next one is the parity generator, but we do not have to focus again in a parity generator because it is not in the mid-sem syllabus. Okay, that we will cover later. Again, this 3-bit parity generator also, it is not in a mid-sem syllabus. So now we have to come to the next topic, which is known as the multiplexer, demultiplexer, encoder and decoder. And that is in our mid-sem syllabus. Okay, I already said the mid-sem syllabus in your group, so you can check that. And there are also some of the topic which we do not have to cover in mid-sem, so skip it. Okay. After the syllabus of the mid-sem 2 is covered, then I will take those topics. So now the next topic is encoder, decoder, mux, demux, or you can say the multiplexer and demultiplexer. So first is starting with the multiplexer and the demultiplexer. Okay, and then we will go to the encoder and decoder. So again, multiplexer and demultiplexer, it's covered in the lab session. So, but we also cover this in a theory session. Okay. So what is multiplexing? Actually, multiplexing means a sharing. Okay. Multiplexer means actually sharing, and in multiplexer, what we have? We have a n to 1 multiplexer. What that means? N to 1 multiplexer means we have a numbers of input, n numbers of input, but at a time only one output. So multiplexer having the n numbers of input but having only one output. Okay, so the transmission multiplexer will take the information from the several sources. Multiplexer will take the information from the several sources, but it will be transmitted to only a single line. It will transmitted by only a single line. Okay. So you can also say it, or also we can also check it in a lab session. Multiplexer is also known as the data selector. Why it is known as the data selector? Because it have to take the data from the several input. It will take the data from the several input, but at a time or at a moment it will allow only a single data to come to the output. Okay, so multiplexer is also known as the data selector. Multiplexer is also known as the data selector. Why? Because it will take the data from the several inputs and it will pass the data to the outputs, but at a time only a single data will come to the output. At a time only single data will comes to the output. So here we have the equation where the m is equal to 2 raised to n. Okay, and here m and n both are integers. We do not have to focus on the fractional part. Now, what is m and n in a multiplexer? So generally, as I already said, the multiplexer is a m to 1. Multiplexer is a m to 1 multiplexer because it will take m numbers of input and only one output. So that's why multiplexer is also known as the multiplexer is also known as a data selector. Why? Because it will take the data from the several input, like you can say the m numbers of input. But at a time, only one data is connected with the output. At a time, only one data is connected with the output. So m is the input. We have only one output I, or you can say y. But suppose I have a numbers of data. But which data is comes to the output? Who select that? So for that we have the selected lines. We have the select lines. We have the select lines. Now what is the role of select lines? Select line will select which input is connected to the output first. Which input is connected to the output first. Okay. So that is the role of the select line. That is the role of the select line. We have a numbers of input. We have a numbers of input, but at a time which input is comes to the output, which input is comes to the output, that is select by the select lines. That is select by the select lines. So how many select lines we require? So for m number of input, we have the equation of 2 raised to n, where n indicates the number of select line, where n indicates the number of select line. Okay. So suppose my select line is 1. Suppose my select line is 1. So here m is the input. So 2 raised to 1. So for one select line we have 2 input multiplexer. Suppose I have a two select line. Suppose I have a two select line. Okay. Suppose I have a two select line. So my number of input is 2 raised to 2. So 4 input. Suppose my select line is 3. So for 3, I have 8 inputs. For 16, I require 4 select line. For 32, I require 5 select line. For 64, I require the 6 select line. For 128, I require the 7 select line, like that. So here in the equation, M indicates the number of input and N indicates the number of select line required. N indicates the number of select line required. Okay. So we have to focus on the 4 cross 1 mux, or you can say 4 to 1 multiplexer. You can say 4 to 1 multiplexer. So what that indicates 4 to 1 means? We have 4 inputs and only 1 outputs, and the multiplexer also is uh, denoted by the mux. Okay, so the short form of the multiplexer, it is mux. So you can say 4 cross 1 mux or 4 to 1 multiplexer. So we have 4 inputs. You can say I0, I1, I2 and I3. So I is denoted for the input. So I have only one output. You can say Y. And for 4 input, I require 2 select lines. For 4 input, I require 2 select lines known as the S0 and S1. Known as the S0 and S1. And we have also one enable pin. Now, what is the enable pin? Enable pin is used to give the energy to whole IC. Enable pin is give the supply to the whole IC. So it is used to give the energy to the full IC. So this is the enable pin. Okay. So now it is a 4 cross 1 mux, which having 4 input and 1 output. And for that, which input comes to the output? Which input comes to the output? It is select by the select line. It is select by the select line. Okay. So we have two select line S0 and S1. So let us make a truth table. So this is the truth table of a 4 cross 1 multiplexer. So when my select line is 0 0, when my select line is 0 0, my I0 input, my I0 input is comes to the output. All others remain as it is. It will not comes to the output. When my select line is 0 1, when my select line is 0 1, my I1 input is comes to the output. All the other three, you can say I0, I2 and I3 is remain as it is. It is remain as it is. Okay. Suppose my input select line input is 1 0. Suppose my select line input is 1 0. Okay, 1 0. Then my I2 input only comes to the output. Then my I2 input is connected with the output. So another three I0, I1, I3 is remain as it is. And when my input is 1 1, when my select line input is 1 1, when my select line input is 1 1, then my output is connected with the I3 input. My output is connected with the I3 input. Okay. So we have a 4 input I0, I1, I2, I3, and at the time which input is connected with the output, then this is the equation. Okay. So from the truth table, we have to draw the logic diagram. We have to draw the logic diagram. So we have 4 input. You can say I0, I1, I2. So this is the equation of finally output. And that equation just we have to implement. That equation we have to implement. So for this is the final output equation is I0, I1, I2 and I3. So when my I0 comes, when my select input or select line S0 and S1 0 0. Select line S0 and S1 0 0. Okay. When my I1 comes to the output, when my select line S1 is 0, S1 is 0, and S0 is 1. S1 is 0 and S0 is 1. So the equation is S1 bar, S1 bar, S0, I1, S1 bar, S0, I1. And then for I2, S1, S0 dash I2, and for I3, S1 and S0. For I3, it is S1 and S0 as it is. Okay. So that equation we have to implement. So let us draw the logic diagram. So before that, you can easily see here we have an equation. So this equation is in the SOP form. So first we have to product. So first we have to use the AND gate, and then we have to use the sum. Then we have to use the sum. For sum we have to use the OR gate. So we required 4 AND gates, which having a input, you can say I0, I1, I2 and I3. And after that 4 AND gates, we have to add those 4 AND gates. So we require the OR gate for the addition. And another IC, we have the 2 input lines, you can say, which is select and line S0 and S1, and 1 enable pin. Okay, and again I'll tell you, it is not compulsory to show the enable pin or enable input. You can also draw the, instead of 4 input AND gate, you can also draw the 3 input AND gate. You do not have to show the enable pin or the enable input. It's your choice. Okay, it's not compulsory. So now for I0, what is the equation? S0 dash S1 dash I0. S0 dash S1 dash. So we have to take the input from the S1 and S0 and connect it with the NOT gate. So here I required S1 bar, here I get the S0 bar. So finally we have the output. For I1, my S1 is 0, my S0 is 1. So you can see I am directly taking S0, but S1 we are connecting with the NOT gate. For S1 we are connecting with the NOT gate. Okay. For I2, we have a S1 S0 bar. So S1 we are connecting directly, and with S0 we are connecting a NOT gate, so S0 bar. And for I3 it is S1 S0. So we do not have to focus on any node or do not have to connect any NOT gate. So this is the logic diagram of the 4x1 multiplexer. So anyone having any doubt in a multiplexer and 4x1 mux? Anyone having any doubt in the multiplexer, or you can say 4x1 mux, you can ask me a question by chat session, or you can ask me a question by unmute yourself. And if you do not have any doubt, please write down a clear in a chat session. Okay, thank you. Again, see, this is the next topic is the logic function generated by using multiplexer. Okay, so these are the examples, but again, it is not in the syllabus of a mid-sem 2. It is not in the syllabus of the mid-sem 2. So we do not have to focus on that. We will cover it afterwards. So this is the example actually, but we do not have to focus on that. Now the next one is the demultiplexer. The next one is the demultiplexer, and you can also say that it is demux. So mux, demux, multiplexer, demultiplexer. So demultiplexer will work opposite to the multiplexer or inverse operation of the multiplexer, you can say. In a multiplexer we have n numbers of input and only one output, but here in a demultiplexer we have only single input. We have only single input and n numbers of output. We have only single input and n numbers of output connected to the demux. So the multiplexer is also known as M cross 1, but demultiplexer is also known as the 1 cross N, or you can say 1 cross M. Okay. So instead of data selector, the demultiplexer is known as the data distributor. Okay. Now, what is demux? You can see in the line, the demux is a device which will take the information by only a single source, and it will distribute that information to the different destination, Okay. So it having only a one input and numbers of output. So again, my equation remains same. M is equal to 2 raised to n. But in a multiplexer, M indicates the number of input. In multiplexer, M indicates the number of input, but in demultiplexer, M indicates the numbers of output. What M indicates? Number of output. Again, the N is also indicated. It is indicating the same thing. You can say the select lines. You can say that, say the select line. So here in multiplexer, M indicates the sorry, M indicates the number of input, but in demultiplexer, M indicates the numbers of output. And in both the equation, N indicates the select lines. So you can see here, demultiplexer is the 1 cross M demux, where M is the numbers of output. M is the numbers of output. And N indicates the number of select lines. Okay, so demultiplexer, let me show you. It's also known as the it is also known as a data distributor. Why it is also known as a data distributor? See, multiplexer is known as the data selector because at the input we have numbers of data, and what multiplexer does, it will select any one data and connect with the output. But in demultiplexer we have only single input, so only single data input. But that data input will distribute the, suppose in demux we have single input only. So this is my data input, you can say. But that input can be distributed to the several outputs. That's why the demux is known as the data distributor. Okay, so this is the demux. Demux is known as the data distributor. It will take a data from the only single and it will distribute the data to the numbers of output. So multiplexer is known as the data selector and demultiplexer is known as the data distributor. Again, we have to focus on the 1 cross 4 demux. As we have a 4 cross 1 mux, but here we have 1 cross 4 demux, and here you can see the D is indicated for the data, O is indicated for the output. So we have only single data input, you can say D, and we have 4 outputs, you can say O0, O1, O2, O3. And the data input is connected to which output first, or data input data is distributed to the which output first. It is select by the select lines. So four outputs we require two select lines. For four outputs we require the two select lines. Okay, so we have two select lines, S0 and S1, and my input is connected to which output, that is select by the select lines. So again, we have to focus on the truth table, and from the truth table we can draw the logic diagram. From the truth table we can draw the logic diagram. Okay. So you can see, suppose my select line input is 0, 0. Then my data input D is connected with O0 only. Suppose my D is 0, then my O0 is 0. Suppose my D is 1, then my O0 is 1. So what is my D? It is connected with O0. My O1, O2 and O3 is remains as it is, or you can say inactive. They are inactive at the time. They are inactive, or you can say a low state, or you can say a zero state. Okay. So when my select line input is 0, 1, then my data input is connected with O1 only. Then my data input is connected with output O1 only. My output O0, O2 and O3, outputs O0, O2 and O3 remains inactive. It will remains the inactive, or you can say a low state or a zero state. When my input is 1, 0, when my input is 1, 0, then my data input is connected with the output O2 only. Then my input data is connected with the output O2 only. My output O1, O0 and O3 is remains inactive. It remains inactive, or you can say in a zero state. So here all are the zeros. Only O2 is connected with D. So here it is denoted by D. And when my select lines input is 1, 1, when my select lines input is 1, 1, then my output is connected with the O3 only. Then my input is connected with the output. Then my input is connected with the output O3 only. All the others, output O0, O1 and O2, O0, O1 and O2 is it remains inactive. It remains inactive. Okay, it remains the inactive, or you can say zero state. So this is the truth table of the 1 cross 4 demux. 1 cross 4 demux. Okay. So again, from the table we have to draw the logic diagram. So here, instead of numbers of output, we have a 4 output. Only single output, we have numbers of output. Okay, but we have only single input, which is D. We have only single input line D. So for O0 output, what is my input? S1 and S000. So here I am drawing two lines. Okay. Or you can also draw the single line, but if you require the, suppose if you are drawing S1 line only, and if you require S1 dash or S1 bar, then you have to draw the NOT gate separately. Then you can draw the NOT gate separately. Okay, so first for the O0 output, my select line is 0 0. So I am taking the input from the S1 bar, I am taking the input from the S0 bar and a D. So you can see here, I am taking the input D. We can take the input from the S1 bar and we can take the input from the S0 bar. Then my output is O0. Then my data input D is connected with O0. When my data input D is connected with O1, output 1, then we have to check the select line. My select line is S10, S01. So again, data is connected to the input, but we require the S1 bar and S0. So I am taking the another input is S1 bar and the third input is S0. So S1 bar, S0. Same way we have to draw the logic diagram for O2 and O3. Same way we have to draw the logic diagram for the O2 and the O3. Okay. So this is the logic diagram. You can see here. This is the logic diagram of the 1 cross 4 demultiplexer. 1 cross 4 demultiplexer. So anyone having any doubt in a demultiplexer? If anyone having any doubt in a multiplexer, or you can say a demultiplexer, you can ask me a question in a chat session, and also you can ask me a question by unmute yourself. And if it is no doubt, please write down a clear in a chat session. Okay, so thank you. So again, tomorrow is Wednesday, and I will take your second lecture. Okay, so because Thursday you have again, I think we do not have a lecture because of the you have another subject session. So I will take your second lectures of the tomorrow, and I will share the link. I will share the link of the lecture in your WhatsApp group. Okay. Yes. See, after the mid sem, no, before the last date of the assignment 2, all the topics was covered. Okay, so do not worry about that. After your mid sem is over, okay, after your mid sem is over, I think your mid sem will be over at Friday or Saturday. I will have to check. I will open all the experiment and all the assignment, also assignment 1 and 2 on the single for the single day. Okay, so if your midterm is all on the Saturday, the next Monday I will open all the dates for the one day only, and those are pending. It's also possible before midsem also, but you have the sessions regularly, so it's your choice. In a single day, you can easily upload it. Okay. Also, that's why I already saw it after the midsem. So you do not have to focus on the time. Either it will take the 15 minutes or 20 minutes. If I'm opening right now, you waste your time to upload it. Okay, so it's okay, Kusi. I will open it for the 2 days. After the midsem, I will open, not before mid. Okay, so and it is as advisable for all the other classes also. So thank you all for attending the session. I will take the your tomorrow's second lecture. So please be present all that because we have a topic to cover for the midsem. So please write down the attendance between 1 to 10, 11 to 20, 21 to 30, 31 to 40, 41 to 50, 51 to 60, 61 to 70, 71 to 80, 81 to 90, 91 to 100. All others, those who are pending, please write down your enrollment number for the attendance. And those who already returned, if they want to leave, they can leave the session and join the another session for the your another lecture. Okay. So thank you everyone. Okay, Amit, I will upload the PPT in e-content and it is already uploaded in Canvas. You can download from the Canvas also.
કે ત્યાં લેક્ચર પૂરો થઈ ગયો, બાય.